Okay, we're back again. Let me just write down what time I should finish this lecture by. Okay, so any questions about anything? Questions? All right, well, that means we can pick it up at the cliffhanger from last time. Okay, so remember what we were up to? I wrapped up the sort of the discussion about the general stuff about the endpoint DFTs of endpoint signals. And, you know, some properties like conjugate symmetry when the signal's real, things like if you have an endpoint signal and you take the M point DFT of that signal, uses an endpoint signal, all you get is like a denser sampling of the DTFT of the signal, things like that. And also, I emphasized both last time and the time before that you can think of the endpoint DFT, you can compute it either of two ways at least. One way is taking x hat of omega hat, the DTFT, and sampling it. The other way is just plugging the endpoint signal x of n into the D analysis and D synthesis. Okay, so you can always find the endpoint DFT of an endpoint signal x of n in two ways at least. And one of them is the one that I call method 1. And this is the way that you can do it on a piece of paper. It's not the way a computer does it. Find x hat of omega hat, the DTFT of x of n, and sample it. So you get x hat of k equals x hat of k 2 pi over tab n for k running over the range 0 through n minus 1. The other way, method 2, just plug x of n into what I call the D analysis equation, which is this. X hat of k equals the sum from n equals 0 to n minus 1, x of n e to the minus j n k 2 pi over n over the magic range. So that's the other way of finding the x hat of k. And at the end of class last time, before the end of class last time, I talked about how you can use endpoint DFTs to do other kinds of computations that you might not ordinarily think of them as being applicable to. For example, showed that if you want to find the convolution of two finite duration signals, you can do that using DFTs. And why is it good to be able to do things in terms of DFTs? Because we have fast algorithms for computing endpoint DFTs, and those are called FFTs. So we started talking about FFTs, and I was going through a specific example of one of these. This is the one that everybody sees first when you read about them. So we started a specific example. And that is the decimation in time endpoint the FFT, or the definition, I guess you don't even say endpoint. The decimation in time, FFT, for endpoint signals, or an endpoint signal, x of n, when n is a power of 2. So n equals 2 to the q for some q bigger than 0, an integer. Okay? All right, to tidy things up, we set psi sub n equal to e to the j 2 pi over n. rewrite the D-analysis equation in terms of the size as follows. X hat of k equals the sum from n equals 0 to n minus 1, x of n, psi n to the minus nk. Okay. That was the cliffhanger. We have this point, and now we take the crucial next step. So now for the crucial step. What we're going to do is we're going to split this sum into two sums of size n over 2 each. This one has n terms in it, cap n terms. Now we're going to have two sums of size n over 2 each. And how are we going to do that? We're going to do it in a really specific way. I'm going to set x sub e of n equal to x of m equal to x of 2m for 0 less than or equal to little m less than n over 2 minus 1. And xo of m to be x of 2m plus 1 for the same range of n values. Okay, so anybody care to guess what E and O stand for? Why I call them XE of M, XO of M? Samantha? Yes. Even and odd. So XE of M is, what kind of a signal is it? It's an n over 2 point signal. And it contains, as its values, the even indexed values of x of n. So x of n values. And xo of m is an n over 2 point signal with the odd ones. Okay. And you can check that this choice of indices exhausts all the values of time in the signal x of n, and since n is a power of 2, n over 2 is an integer. Okay? So this makes sense. The n over 2 minus 1. Okay? So now let's split the D-analysis equation into two pieces, one of which involves xe of m and one of which involves xo of m, as follows. So rewrite D-analysis as follows. X hat of k equals the sum from n equals 0 to n minus 1, where n is even, of x of n, psi sub n to the minus nk, plus the rest of the terms, which is the sum from n equals 0 to n minus 1, where n is odd, x of n, psi sub n to the minus nk. Re-index the n in the even sum as 2m, re-index the n in the odd sum as 2m plus 1, and you get this. The sum from m equals 0 to n over 2 minus 1, x e of m, psi sub n to the minus 2mk. And in the other sum, you get this. M equals 0 to n over 2 minus 1, xo of m, psi sub n to the minus 2n plus 1k. Okay, and the way we did this, for this one here, we set n equal to 2m in that first sum, and we set n equal to 2m plus 1 in the second sum, and you can see that That's how the indices run. They run from 0 to n over 2 minus 1, and you get those terms. Okay? Now, notice, one thing we noticed last time was the following. So we noted last time that if you take psi n squared, that's equal to psi sub n over 2. Okay, we did the proof of that last time. It's just a one-liner. Remember, what is psi n? It's equal to, wherever I put it there. If you take that squared, you can think of it as putting an over 2 in the denominator with the n. So you get psi sub n over 2. Thus, we can simplify further. And I'll put simplify in quotes because maybe some of you out there don't think this is simpler than that, but anyway. To this, x hat of k is equal to the sum from m equals 0 to n over 2 minus 1, x e of m, psi sub n over 2 to the minus mk, plus the sum from m equals 0 to n over 2 minus 1, x o of m, and actually I want to factor something out of that, psi sub n to the minus k, sum from m equals 0 to n over 2 minus 1, x o of m, psi sub n over 2 to the minus mk. And that holds for k's over the magic range, 0 through n minus 1. Now, why do we do this? Well, essentially what's going on here is this first sum is going to compute an n over 2 point DFT of the n over 2 point signal XE. The second sum is going to compute an n over 2 point DFT of the n over 2 point signal XO. That's what we're doing. We do, to make sure everything works out, we have to do some bookkeeping. So after some easy bookkeeping, what we find is the following. We find that x hat of k is going to equal what? It's going to equal x hat sub e of k, actually not quite k, but k mod n over 2 plus psi sub n to the minus k x hat o of k mod n over 2. And that's going to be for all the k values. Essentially what's going on here is, here's the reasoning. The first sum in the previous equation is essentially x hat e of k, almost. That's what the bookkeeping takes care of. And the second sum is almost x hat o of k. And this is something, I don't want to spend too much time on the bookkeeping thing. So the bookkeeping gets rid of almost. Okay, so this is something I don't want to spend a lot of time on. It's easy. You know, I can do a handout for you if you want. You can even look in the book. I don't particularly like the way the book does it, as I don't like particularly the way the book does a lot of things, but whatever. Okay. Now, what's good here? What's good here? What we've done is, and as I said, Peter Dorshuk, my colleague, Professor Dorshuk, loves to call this a divide and conquer kind of way to proceed, because that's what we're doing essentially. We have taken the computation of an n-point DFT, and we have turned it into the computation of two n over 2 point DFTs plus an assembly procedure as dictated by that equation up there. So the end result here, and you're not supposed to see why this is a good thing yet. You'll see in a minute. Okay. The result is we have turned the computation of one endpoint DFT into two phases. First off, the computation of two n over 2 point DFTs and their assembly together by means of that equation up there. So assembly process that takes one of the n over 2 point DFTs and adds psi sub n to the minus k to the second one. Okay? All right, so why is this good? Why is this good? Well, what we have to do is we have to figure out computationally how it introduces savings. And here, in my opinion, the book does a really bad job, in my opinion, counting up computations, because they don't talk about what is sort of the fundamental unit of computing computational complexity nowadays, the so-called multiply accumulate or MAC operation. How many people have heard of a MAC operation? Not too many. Not too many. Well, let's talk about that. So let's see how this helps computationally. Okay. So here's a little aside. Fundamental computation for figuring out complexity, or let's say for our purposes, is a so-called MAC operation, or multiply and accumulate. And I think everybody sort of knows, at least intuitively, that multiplying things inside a computer is what takes the most time. Adding things doesn't take as much time as multiplying. So what is a MAC operation? So MAC is equal to multiply and accumulate. Okay, so what's the idea here? The idea here is, if I have a sum like this, say sum from, say, how about n equals 0 to n minus 1, alpha sub n, beta sub n. Okay, that's a typical kind of thing that arises, and obviously that kind of thing is arising here as well. This involves how many operations? Well, in terms of multiply and accumulate, so this requires nominally n multiply and accumulates. How come? Why? All right, so here they are. Alpha 0, beta 0. That's the first, or 0th, of the MAC operations. Then alpha 0, beta 0, which you already have, plus alpha 1, beta 1. So you already have this. This is one multiply and accumulate. And this is the multiply, and this is the accumulate for the second operation. And then the next one is something you already have. Alpha 0, beta 0 plus alpha 1, beta 1 plus alpha 2, beta 2. You already have this, so you have to compute this multiply and then this accumulate, etc. So computing a sum like that nominally requires n multiply accumulates. Why do I say nominally? Because some of these multiplies might be trivial. Like, for example, one of the alpha n's could be 0 or 1. Okay? So that wouldn't involve a non-trivial multiplication computing the next term. some of the additions, some of the accumulates might be trivial because of the zero thing. Like the next term might be zero, so you don't even have to do anything. But nominally, for generic alpha n, beta n choices, this takes n MAC operations. Okay, so let's see how many MAC ops does it take nominally to compute an n-point DFT directly using the D-analysis equation. So how many MAC ops does computing an n-point DFT directly using the equation D-analysis require? Okay, anybody? Let me write D-analysis down again, just so you have it up there. Actually, there it is. So I'm just going to leave it. This is D-analysis. That was convenient. See, this is the kind of thing, I would never do that if you were actually in the room, you know, taking notes and whatever, when you couldn't pause me, but now you can just pause me and you can write that down again if you want. So this is D-analysis. All right, so I want to compute x hat of k given x of n using this equation. How many MAC ops does it take? Come on, somebody. Somebody. Okay, n, he says n. Well, I just wrote that up and I said it requires n max, right? So you look at this equation, you say, oh, it's a sum just like that, so nominally it requires n mac operations. What's wrong with that reasoning? It's a good start. Okay, Alex? Yes, you have to compute x hat of k for all these k values, and each one of those computations is one of these. So there are n computations, each of which requires n max. Therefore, nominally, you need n squared max to compute x hat of k using these equations. So the answer is n squared nominally. And again, the nominally comes from the fact that some of these are trivial. You know, psi n to the minus nk, when k is 0, those are all ones. So the first one is just an addition, a bunch of additions. There's no multiplications required. So note, some ops are trivial. For example, when k equals 0, you're just doing an addition, x of n values. But that's what this nominally, that's the weasel word. The good weasel word here is nominally. That covers up, sweeps under the rug, whatever that difference there. Okay, so n squared. It takes n squared operations to compute an n-point DFT directly. So that's the mantra. So direct computation of the n-point DFT via analysis equation, D-analysis, takes n squared mac ops. Okay, so back to the theme here, that what we did when we did that crucial step of splitting the sum is we took the computation of one n-point DFT and turned it into the computation of two n over 2-point DFTs plus this assembly process. So let's see whether that helps in a computational sense. Obviously it does, or we wouldn't even be doing it, but what the heck? Let's pretend we don't know the answer. Chalk is becoming rare in this room, and this box that I borrowed from the room down the hall has only 3 pieces left. So we're going to be, I'm going to have to go break into Phillips and get some chalk out of Phillips 219 or something. But anyway. So what did our first divide and conquer move do? So our first quote-unquote divide / conquer maneuver turned that thing into two n/2 point DFTs and an assembly process. So it turned n squared into what? Well, you have two n/2 point DFTs. So this is nominally, of course. So that's going to be 2 times n/2 quantities squared. But there's also the assembly process. What is the assembly process? The assembly process is this. For each k, you have to take xe hat of k mod n/2, xo hat of k mod n/2, multiply the second term by this, and add them together. That's one MacOp. Okay, plus n. So this is the nominal computational complexity, or the nominal max for an n/2 point DFT, and this is the number of max for the assembly process. And why is there n of them? This is something, for some reason, this slips under people's radar. There's n of them because for each k, running from 0 to n-1, you need to do something plus psi n to the minus k times something else. And that's one MacOp. All right, so that's the number of MacOps nominally required to do it, having done this divide and conquer maneuver one time. Now you may say, well, is this better than n squared? You can show really easily that this is less than n squared, at least when n is bigger than 2, which n always is in real life. So this is lower than n squared when n is bigger than 2. So we have an improvement. But you might say, okay, well, having done that, why stop there, right? Why not divide and conquer on the two n/2 point DFTs? This looks like an L. Let's make this clearly a 2. Why not do divide and conquer on the two n/2 point DFTs? And see what happens. So let's do that. And continue doing that. Why stop there? Let's do divide and conquer on the two n/2 point DFTs that we've got. So what's that going to do? That's going to turn the n/2 squared each of those n/2 squareds into what? Into 2 times n/4 squared. And remember, n is a power of 2, so n/2 is still an integer, so is n/4 until we get to the end, plus n/2. And so all told, what we've done is this. So 2 divide conquer steps turns n squared into 2 of these, so that's going to be 4 times n/4, the quantity squared, plus n plus n. Because you have that plus n trailing there. If you keep this up, if you do this q times, you can do this all the way down until n is equal, well, until this denominator turns into a 1. So you keep this up, and you can do it q times, and remember what q was, if you've forgotten what q was, so recall n is just equal to 2 to the q, and you end up with this. That n squared ops that you started with turns into, and what's happening here, this is building up by multiples of 2. So you have 2 after 1 step, 4 after 2 steps, and so on. After q steps, you have 2 to the q. In here, you have 1. And over here, you have q n's, because you add on another n every time you do a step. This is just n. Q is log to the base 2 of n. So this turns n squared into n plus n times log to the base 2 of n, because q is log to the base 2 of n. That's the difference. If we do this, if we do this divide and conquer process, and clearly this is tailor-made for recursion. You know, you can have a recursive function, say in Python, where you have a function called like, oh, don't even bother. You know, like dft of x comma cap n, and you do that, and then you do divide, and then you set n to be n over 2, and then you recurse on that kind of thing, right? Easy to write a routine to do this. But you may say, okay, well that, you know, is that really better? Well, yeah, it's a lot better. It's a lot better when n gets large. So this is a huge savings when n is large. And for example, like, say if n is 1024. Okay, remember n has to be power 2. And 1024 is a power 2, right? So, for example, how about if n is equal to 1024 equals 2 to the 10th, so q is 2, then n squared is equal to what? Now, let's see if I can do this in my head. It's going to be 1,048,576. How many people think I actually did that in my head? Okay, well that's a compliment, Brendan. I appreciate that, but I actually didn't. I memorized it, and I always thought it was kind of cool that if you take 1024 squared, then the first 4 digits of that are 1048. Why should that be? Anyway, okay. Well, that's what is n plus n log n. N is 1024, n log 2 of n is 10,240, so this is going to be 11,000. This one I am doing in my head, or I am doing sort of on the board. So 10,240 plus 11,000. No, 1024 plus 10,240 is 280. Oh, frick the heck with it. Okay, 1024 plus 10,240, 4, 6, 2, 11, 264. Is that right? Yeah. Okay. So look, it's a factor of 100. When you just go out to 10, q equals 10, you already have a factor of 100 difference, and this gets really big. This difference gets really big the bigger n gets. Okay, so this was a major breakthrough, the FFT, and it spurred a lot of developments, and like I said, FFTs aren't just good for signal analysis, they're good for data science, they're good for machine learning, they're good for figuring out convolutions, whatever. So this motivates, okay, the existence of FFTs. So one sort of submoral of the story is the following, that any computation that you can recast into DFTs, you can probably save on doing that computation. So by recasting computations as DFT comps, you can often save big time. And no, remember I said that, the example we did last time where we had the computing a convolution of two finite duration signals using DFTs rather than directly. I said, look what we're doing. We're taking DFTs, doing a simple functional multiplication, taking inverse DFTs. And you may say with some justification, wait a minute now, all you did was show me that you could reduce the computations in computing a DFT, the D-analysis equation, by doing this divide and conquer. How about the inverse DFT? Well, that's the same thing essentially, the same computational essentially as the forward DFT. So comment, I alluded to this last time and I forget whether I wrote it down, but I want to make sure I do write it down, that computing an inverse endpoint DFT via the equations that we've been calling desynthesis. And let's just write that down just so you can see what it looks like. And why it's so similar. So it's going to be x of n equals 1 over cap n, sum from k equals 0 to n minus 1, x hat of k, psi sub n to the positive nk. And this runs over n values. That is essentially the same computation as this. The only thing is you got this 1 over n out front, and that's just some trivial one multiplication you do at the end, or n of n actually, but forget about it. And you have a positive exponent there, so you have essentially psi sub n instead of psi sub n inverse as your fundamental thing. So this is essentially the same computation as finding x hat of k via d analysis. And some people, like, they really have this, they want it to be symmetric, so they do both, they define it so you have a 1 over square root of n in both directions. I prefer not to do it that way. Professor Wagner does it that way. So no knock on him, it's just his preference. But anyway, so that's the deal. There you go. That's the FFT. And any questions about it before we move on to talk a little bit about spectrograms, again, in a little more depth than we were able to earlier? Okay. All right, so now, make a nice left turn here. I want to, and this is going to wrap up the material in chapter whatever it is. What are we in now? This is chapter 8, chapter 9, I forget. And I don't have the book with me, so I can't check. I don't even have my computer. I don't even have my folder full of notes, anything like that. So this is a pure extemporaneous performance here, done in one take, as all the lectures are. But anyway, okay, so one more topic before moving on to IIR systems, and that is, so next topic, and that's DFT related, is first I'm gonna set up the umbrella, and then I'm gonna look under the umbrella at a specific example of what we're gonna be doing. The umbrella under which all this follows is time frequency analysis. time frequency analysis. And the specific version of time frequency analysis that we're going to look at is going to be the spectrogram, which we've already met over the course of the semester, at least a little bit. Okay, so what is time frequency analysis, and what else falls under the time frequency analysis umbrella besides, say, the spectrogram that we're going to talk about? Well, an example of something else that falls under there is wavelet analysis. Okay, and I actually talked really briefly earlier in the semester about using wavelets in signal processing, and as it happens, like the MP3 standard uses wavelets, whatever, it's a data compression technique. That's another thing that falls under the time frequency analysis umbrella. But here's the example to keep in the back of your mind. Suppose you had two pieces of music. Okay, so imagine these two pieces of music. And music is always a good thing to keep in the back of your mind. In fact, while we talk about this, I'm always going to say, if you have a melody, then this is what's happening, whereas if you have a chord, then this is what's happening. So get your mind thinking about music, hearing music, whatever. So these two pieces of music. Say, let's call one of them x1 of t. These are continuous time signals. Okay, x1 of t is going to be a 1 minute A440 followed by 19 minutes of silence. Okay. x2 of t is going to be 19 minutes of silence followed by 1 minute A440. Okay. And I'm assuming here that both of these signals are silent before and after the activity. Okay. All right. Now, suppose I sample those guys, sample them really, really fast, as fast as you want. So say we sample these guys. Fast as you want. You're going to get two discrete time signals, x1 bracket n and x2 bracket n. The question is, what are their DTFTs going to look like? How are they going to be related to each other? Well, it turns out x1 hat of omega hat, so their DTFTs, are related by x1 hat of omega hat is equal to sum e to the minus alpha omega hat times x2 hat of omega hat. And this is for some real number alpha. And in fact, alpha is going to be an integer if we play our cards right. Why is that the case? Anybody? Oh, they're not brackets. Okay, let me put them. I'll put it on the next board. Okay, so. Actually, and I'm going to write it this way instead. So x2 hat of omega hat is going to be equal to e to the minus alpha omega hat times x1 hat of omega hat for some, turns out to be positive alpha. Okay? And you can see sort of why. This is because time shift rule. for DTFTs. X2 is just X1 shifted by 19 minutes to the right. So alpha is going to be some related to 19 minutes and the sampling frequency and all that stuff. So what does that mean? So that means the magnitude of these guys is, how are the magnitudes of these related? Magnitude of x2 hat of omega hat, which is often what you plot to get an idea of what the frequency content of a signal is and where it's focused, the magnitude of x hat of omega hat, x2 hat of omega hat, is going to be equal to what in terms of the magnitude of x1 hat? Okay. Alicia. Yes, thank you. Okay. E to the minus alpha omega hat. Oh, J. There's a J in there. I'm sorry. You must have known that my J was missing because it wouldn't have been right without the J. You did. Okay. Pretend you knew. Pretend you knew, because I like that answer. Magnitude of this is equal to the magnitude of that. And that's because magnitude of e to the minus j alpha omega hat equals 1. E to the j theta has magnitude 1 for all real theta. So, by graphing the magnitudes of these, measuring the magnitudes of the spectra, you can't tell the difference. You can't tell which signal it was you were looking at. So, and therefore, so hence the magnitudes of the DTFTs tell us nothing about which signal we're looking at. They don't distinguish between these two very different signals. So if someone came up to us in Hope Plaza and showed us a magnitude plot of the spectra of X1 and X2 events, and I'm trying to decide, which signal did this come from? The A followed by silence or the silence followed by A? You would have no way of answering that question. The difference between them is buried in this phase term. It's buried in this e to the minus j alpha omega hat term. So the difference, the distinguishing feature thing, is the phase term. And that's, in some sense, that's the graveyard in which the difference between these two signals is buried. And why is it hard to analyze that? So it turns out that even if you know the phase term, computationally it's really difficult to deal with, because the larger alpha is, the faster this phase twists around 0 to 2 pi. So especially for large alpha, that this phase term is hard to analyze. It involves much more resolution. So you need way more, computational numerical resolution than usually available, etc. And I'm, like I said, sometimes some of this stuff, when we're talking about the spectrograms and the time frequency analysis, I'm going to give you a broad brush look at the story, so you understand sort of why we're doing it. Okay. So then usually available. Okay, roughly speaking. All right. So the point is, you only know the phase modulo 0 to 2 pi, and so as alpha gets bigger in omega space, that phase changes much more rapidly around 0 to 2 pi, and counting how many times it changes is what's going to give you the alpha there. And that's hard when it changes really fast between two different omega hats values, which is what happens when alpha is big. You can't resolve those two. So anyway, that's what's going on there. All right, bottom line, and also, if you took these are DTFTs, but if you took the endpoint DFTs of these signals for any end, that's not going to tell you anything more, because those are just sampled versions of these DTFTs. So the bottom line is, just doing Fourier analysis does not help you understand the difference between these two signals, at least in a practical sense. So the bottom line, we need something beyond, we need a tool beyond just spectral analysis to get a better picture of what's going on with signals that differ in this kind of a way. So specifically, to get a better idea of not only what's happening, and I'm writing a lot of words here, hope you don't mind. I always get kind of wordy at this point in the class. A better idea of not only of what's going on spectrally, I'll put that whole phrase in quotes, with a signal, but also when it's going on. Okay, so we don't just want to know that this signal has a high frequency content around 440 hertz, or omega 0 equals whatever it has to be, depending on sampling frequency. We want to know when that A440-ness happens in those two signals. And that's what time frequency analysis is for. That's the umbrella under which the spectrogram falls. Okay. So the tool, the math tool that we're going to use to define spectrograms, it's something called the short time DFT. And this is something that involves user choices, and all the user choices have different consequences. Some of the consequences trade off against each other. This is always good. This is always going to happen in engineering life. You know, user choices, you make a choice of this guy, which makes this thing do well, but oops, it messes up this thing, so I have to change that user choice. This comes up a lot in spectrograms. So a lot of it, you end up, if you want to get a good one, you have to play around. But anyway, the math tool that we're going to be using is something called the short time DFT, or STDFT. That's what the book calls it, short time DFT. All right, now, this is complicated. This is somewhat complicated, but not impenetrable. The thing is, it involves a lot of user choices. So it involves several user choices. Okay. And all those user choices trade off against each other. So what is the setting? What is the ambiance in which a short time DFT takes place? So here's the setting. And this is just for definiteness. You start with some continuous time signal, or at least a continuous time signal over some range of values. And you sample it, so you sample some continuous time signal for a while. Should a while be one word or two words? I think that I'll leave it as one word for now. All right, you sample a continuous time signal for a while, and you can just assume the sampling is fast. So do it fast. If you want, assume the signal's band limited and you're sampling faster than Nyquist rate. So assume faster than Nyquist if you want. But, you know, anyway, the point is you end up with a long discrete time signal, which I'm going to call X event. So if you like, so you end up with a long discrete time signal, X event. All right. Now start the user choices. And I'm looking at the timer. I'm wondering how far I'm going to get on this today. It's going to be about, we have about 13 minutes, 12 to 13 minutes left. So that's really more like 10 minutes left. No, wait. No, good. 17 to 18 minutes left. So that's more like 15 minutes left. Taking into account the 3-minute break, which we're not doing unless I feel like it. So anyway, see how far we can get with this. All right, so now for the user choices. Okay, so the first user choice is going to be a sequence of what are called analysis times. So first off, you have a sequence of analysis times. You'll see what role they play as we go along. What are these analysis times? So a generic analysis time, we're going to denote a generic analysis time as n sub s. And all that has to be true about these analysis times are that they increase monotonically to infinity or to at least whatever the length of the signal x of n is. Generally what's going to happen is they're going to be multiples of some fixed integer cap r. So these are positive multiples of some fixed integer cap r. So that means that they are going to be, the list of them is 0, r, 2r, 3r, and so on, however long it has to go. Okay, so these are analysis times. Okay. Next thing we do is pick what we call analysis window length capital L, and a windowing function that's an L-point signal. So an L-point windowing function that I'm going to call W of n. And what kind of windowing functions are allowed? Well, any L-point signal will do, but the ones that people like to use are like rectangular. We talked about these a couple days ago, or a couple lectures ago. Rectangular window, Hamming window, Hahn or Hamming window. So this is rectangular, Hamming, Hahn, whatever. Okay? And the constraint on cap L, okay, is going to be that it's bigger than or equal to R. So we need to have L bigger than or equal to R. And generally, L is like 2R or 1.4R or something like that. So usually it's more like L equals 2R or 1.07R or something like that. And we'll see what the various consequences of choosing L closer or farther away from R is. But the reason, it's going to turn out the reason we need L bigger than or equal to R is, what we're going to be doing is we're going to be analyzing the signal over windows of length L that begin at the analysis times 0R, 2R. So the first window is going to be of length L. We want to make sure we capture every point in the signal in at least one analysis window. So we're going to need that the window at least overlaps the next analysis time. Okay, that's why we need L bigger than or equal to R. Okay. Now we're also going to pick a cap n bigger than 0. And in fact, cap n is going to be bigger than or equal to L. So an integer cap n bigger than or equal to L. And this is one, the bigger, the better. But bigger requires more computation. So bigger n implies better. You'll see why later on. We'll see why. So as we'll see, but more computation. Okay, so now we've got our user choices in the short time DFT. How do we define the short time DFT? All right. And the notation just gets, forgive me, this is the way it goes. Okay, so for each ns, what are we going to do? We're going to define, I'm going to write, I can never, the reason I stalled there for a second is I can never decide whether to describe what we're going to do and then write the equation, or write the equation and then describe what we're doing. So I've decided to write the equation and then describe what we're doing. So each ns define x hat bracket, and let's call it k comma n sub s equal to the sum from n equals 0 to n minus 1, here's where the cap n comes in, of w of n, x of ns plus n. And we're going to do this for each k value between 0 and n minus 1. Okay, so I'll let that burn in your eyes for a second or two. And by the way, I just want to mention the book uses k comma ns. I'd prefer to use ns comma k, but I'm overruled. All right. So what is happening here? What is happening here? All right. Oh, I forgot something important. Sorry, guys. E to the minus j n k 2 pi over n. All right. So now I have to let it burn again. Okay. Now that I fixed it. So what is going on here? Clearly, there's something DFT-ish going on, right? Because you got that e to the minus j n k 2 pi over n thing going. And a sum from 0 to n minus 1. It looks an awful lot like a analysis equation, D-analysis equation. But you've got this ns, you've got this ns plus n, you've got this w going on. What is happening here? All right, so here's the idea. If I take the windowing function w of n, remember that's an L point signal, that's a rectangle, and you might as well think of it as a rectangular window. It could be a Hamming or Hahn window. And you multiply it by x of ns plus n. What does that give you? That gives you the values of x of n between times ns and ns plus l minus 1 inclusive. And after that, it gives you zeros. So w of n, x of ns plus little n, 0 less than or equal to n, less than half n, is an endpoint signal, but it's also an L-point signal. So in fact, it's an L-point signal because of W. So that's because W of n is equal to 0 when n is bigger than or equal to L. And what we're doing on the right-hand side of this equation is taking the cap endpoint DFT of that signal. So the right-hand side, RHS, of this equation is computing the endpoint DFT of this signal. Okay? And this is true for every one of the analysis times in sub s. So I'm going to draw you a picture in a sec. So this is true. This characterization is true for each analysis time ms. Why can't I spell? Sometimes. Individually. Okay? So what are we doing? Just thinking of it in terms of a procedure. So procedurally, what do we do? All right. You go to an analysis time n sub s. So remember the user choices, n sub s is our first user choice. So usually they're going to be multiples of some fixed cap r. So say I go to analysis time 17r, all right? I'm there. What do? I take my windowing function and I plunk it down to start at that analysis time, and I look at the x values in that window, starting there and going to the right by L minus 1. So you window, using your windowing function, little w of n, window the signal x of n, starting at n sub s, ending at n sub s plus L minus 1, because w of n is a windowing function, and the result of that is an L-point signal. Whose values are w of n, x of n, s plus n, 0 less than or equal to n less than L. Okay, so I've windowed my x of n, starting at analysis time n sub s, L to the right. Now regard that L point signal as a cap n point signal. Remember, cap n is bigger than or equal to L. See? And take its endpoint DFT. So you regard that L point signal as an endpoint signal by a zero padding, and you take its endpoint DFT. And that will give you x hat of k, comma, n x. 0 less than or equal to k less than n. All right. So that yields x hat of k, comma, n s. 0 less than or equal to k less than n. All right. That whole thing, the user choices through that equation, through the explanatory idea and the procedural description of what's going on, that's the short time DFT with those user choices. Okay, so that's that whole thing. So user choices through the sort of procedural explanation is the STDFT. And that is the basis for the spectrogram. That's the foundation on which the spectrogram is built. So this is the foundation of spectrogram. And it doesn't make any sense to start talking about the spectrogram with like 3 minutes to go. So I'm just going to stop it there for today. First, ask if there are any questions. Since we have a minute or two left to have questions. Alex Backrow. Yeah, I mean, okay, the question is the Shazam project uses this kind of spectrogram? Yes, it does, but it uses a built-in MATLAB function to compute it. And I think I might do a little video on the Shazam project. And in fact, if you're watching this lecture late enough in the semester, I might have already done that video, but I haven't done it as of real time today when I'm recording this. So I'm thinking about that. Okay, so that's a good question. Jack? Okay. The thing is that the original signal, okay, the original continuous time signal, remember I said, I was kind of casual about this, right? You sample some continuous time signal for a while, you do it fast, assume faster than Nyquist rate if you like. And you're right. A finite duration signal in continuous time can't be band limited, it turns out. And so there's no such thing as a Nyquist rate for one of those. But just pretend it's band limited, and don't be so picky. Sorry. I know, CU air, you don't want to be flying things that fall out of the air. I know you have to be careful, but anyway. All right, we good? Okay, so I will see you next time, and we'll figure out how this short time DFT builds into the spectrogram. And now I have to go through the awkward process, the multi-click process of stopping the video. So this, followed by this, followed by this, followed by, I forgot to say, I really miss you guys, and I hope you're doing okay, and I'll see you soon.